So if one of its strings is satisfies all these three conditions, then B will accept that X. It'll accept that X. Okay, now a bit of a complication. Now this machine B, it's not constructed to actually run on some input. This may be a common confusion. This is a comment by Sipser. This is Sipser saying, this is not me. Okay. So what is, if that's the case, that might seem a bit puzzling. So what is B for? Why is it constructed? Well, its function, its purpose is that once it's constructed, it's encoded description. And so you need to construct it to be able to encode its description. You need to know what it is before you can describe it. Okay, common sense. So you construct your B, and then you have your angular brackets B. That's the encoded description of B, and then you'll feed that encoding into the Turing machine that decides ELBA. Okay, that's part of the reduction. It's part of the reduction strategy, right? Okay, so this B, it doesn't actually get used. It's just it got built so that its encoding can be fed into the Turing machine that decides the language ELBA. Right? Okay. So note that another complication. Like I say, the proofs are getting harder. Okay. Now, all right. Now, once the Turing machine that we assume to exist that decides the language ELBA, okay, because you've given it now the encoded description of B, this machine that whose language is the set of all positive accepting computation histories when the string W is fed into the LBA begin. Right. Okay, so this Turing machine, it will return its answer. So what's going on there? Well, we've assumed this Turing machine exists because in the very beginnings of the proof by contradiction we assumed the opposite, remember? Therefore, the language ELBA is decidable. Therefore, it's a Turing machine that decides it. And now it's that Turing machine that we're talking about here. This deciding Turing machine. Now that deciding Turing machine will look at a string, and what is that string? It's just the angular brackets of B. Okay? And that this decider, this Turing machine, will reply. It will say, oh, for this machine, B, it will say it will either accept or reject that encoded description B. Right? Okay, now if it accepts, now we have to go back to the logical skeleton, the first square. Okay, now if it accepts, now remember, now there's at most one string in that the language of B. Okay, so if let's see. So if this Turing machine here, if it accepts this language here, that means there's zero string. There are zero strings in that language. Okay, L of B is the empty set. That Turing machine accepted that. In other words, the language of B, L of B, is empty. Right? Now what is B? Well, it's what is the language of B? What is L of B? It's the set of strings that are the accepting configuration histories. So if those histories are 0, if there are none of them, that means that the Turing machine M did not accept. Okay, so it rejected. And if this this Turing machine here returns a reject, so what does that mean? Well, that means there was one string in the language. Yeah, that's not 0, so it rejects. The Turing machine rejects. So so there was one string in the language. And what does that mean? Well, it means that there was one string, there was one accepting configuration history. And that means that M accepted W. So we now know M accepted W, right? So either way, either M rejects W or M accepts W. So if this decider rejects, then we can conclude that M accepts W. And if this decider accepts, then we know that M rejected W. So whatever this Turing machine does with this language, the M will do the opposite with W. Okay, so we'll invert it. Hope you follow that. All right. So here, yeah. So once this decider, in other words, the Turing machine that decides E LBA, okay, whatever its answer is, accept or reject, then we just do the reverse to get what the answer that M would do. Would M accept W? So if the Turing machine for ELBA accepts, this will reject W. If the Turing machine for ELBA rejects, then M will accept. Okay. So either way, we've got a decision, if you like. M is actually deciding. Right? M will actually decide whether it accepts or rejects W. Okay? So in other words, we can decide this language. And that's a no-no because we know that this language is undecidable. Okay, that's our contradiction. Finally, we've got our contradiction. Right? And so since this is our problem A and that's our problem B, and we reduced this to that, okay. Why do we do that? Well, because to solve this problem, we used the solution to this one. And what's the solution to this one? Well, B. Well, actually, the encoded description of B. Okay. So the solution for this one was the use of the encoded description of B. Okay. That enabled us to decide this. Okay. So this is problem A and that's problem B. And so we reduced problem A to problem B. But we know that problem A is undecidable, and therefore this is undecidable. And that's what we really want. Right? We're trying to prove that this is undecidable. Okay? And we know it's undecidable because we reduced from this problem to that problem. Whew. Okay, so next session we'll actually do, now this is all proof idea, right? So then we make it a bit more rigorous with the actual proof, but we've done the guts of it by verbally at least with the proof idea, so I hope you'll find the next fairly quicker. Ciao.